All right, welcome everyone to the AATN seminar today. Our speaker is Stefan Hough, who will be talking about topological data analysis and industrial automation. The floor is yours.
Thank you very much. Thank you for having me. Very glad to be here. So I can talk about a bridge between two fields, right? We have the topological data analysis field and industrial automation. And I think for this audience, it totally makes sense to add some context to what I mean by the automation industry. Okay. So some context. So systems in the automation industry, they are of a very strict hierarchical structure. We have something that we typically call the shop floor, where we have industrial machines like NC machines or injection molding machines or robot cells, where the value stream goes through, so to say. These are controlled by some controllers, which are called programmable logic controllers. And we have subordinate systems like supervisory control and data acquisition systems and so on. So I tell you that in order to sort of draw a picture about the following situation. These industrial machines are very hierarchical and optimized for repetitive tasks. Okay. So an injection molding, for instance, it repeats itself in its operation to produce goods in the very same way in a cyclical sense. Okay, highly repetitive and right. Okay, and that has implications for us because in the so-called discrete automation, as I explained before, is about repetitive processes. This is an old slide of mine now. It's 3 years old. Always bring the same slide, which tells the following. If you consider the state of a machine, whatever that means to you, like 100 parameters describing in what state the machine is right now. Let's call it the state vector. If you consider the state space, which could be, I don't know, 100-dimensional or 1,000-dimensional, then the state performs an evolution over time, traces out trajectory, the state space trajectory. And those are cyclic due to the repetitive nature of discrete automation processes. Or at least in a certain subspace, they are cyclic. And that enables us, at least in principle, to record such a time series, such a trajectory over time, where you capture a couple of repetitions and then model it through machine learning. A statistical model, the distribution of state space trajectories. And those trajectories are then typically contained in some holes, and might be narrower there and wider there, doesn't matter so much. This is sort of the hose of benign state space trajectories. That leads, I would say, at least at first, to 3 fields of applications we're interested in. It leads to anomaly detection, which essentially means if you leave this hose of benign trajectories, this is an anomaly, or maybe put more in a probabilistic sense, if you have a PDF density function of the distribution, then a low likelihood indicates an anomaly, so to say. We can maybe talk about generative models, like generating artificial trajectories, which allows you to erect so-called honeypots, which are sort of black boxes that from the outside look like realistic machines. And if there's an attacker in the cybersecurity setting that interacts with the honeypot, then this is a signal for an intrusion. So use them for intrusion detection systems. And the third type of application would be if you're interested in the learning task, learn how you need to control certain parameters to keep the trajectory within this hose, right? And we are within the domain of process control, and we could talk about reinforcement learning and stuff like this. But in any case, there should be plenty of potential for TDA to be useful. So that's sort of the setting. This is what we did the past 2 years, 2.5, almost 3 years. And within this time, we also built up a whole testbed, a realistic testbed of a production scenario. Here we have 3 such machines, which are injection molding machines, and 3 robots that take out the goods, put them on a conveyor belt, and a 4th robot palletizing them, and so on. And we implemented that with real hardware. What's not real in our case are those machines, actually. So we simulate the thermodynamics, the material flow, other physical processes are simulated, but the controllers, the software, and so on, this is all real. and we use hardware-in-the-loop simulation for the physical processes. Okay, that was quite some work by a couple of people in the last 2 years. And yeah, this was possible because we are a very interdisciplinary team and we are very close cooperation partners, company partners, and it enabled us with software and so on. Okay, so this is sort of the context I want to give you. Now the question is, are there TDA applications in manufacturing, or how do they look like? And, to this end, we published a survey last year, and we did this together with the group in Graz, Michael Kerber. And back then, also Barbara was part of this group. She then moved to US, University of Albany, and Martin is a PhD student in my research center. And the title of this survey is TDA in Smart Manufacturing. So what we did is the following. We performed some systematic, exhaustive literature review. That means we defined a set of keywords that captures what we call TDA, which would be topological data analysis, UMAP, mapper, and precision homology. And we defined a set of keywords that sort of sample form the shape of industrial manufacturing. And today everything is smart, so we find a lot of literature on smart manufacturing, so you better add it to the keywords, right? Like you look for factory automation, operation technology, industry 4.0, and so on. Okay, so these are the keywords, the domain and the method side. The intersection sort of shapes TDA in smart industrial manufacturing. Then we form search phrases of the form domain and method, and you plug in your domain keywords and your method keywords and all combinations, pass it through 5 search engines, ACM, IEEE, and so on. And we got 7,000 results. Those were then filtered, removing duplicates, only focusing on peer-reviewed journal and conference papers, only in English, only where full text is available, so we could dig into the material, check whether the context is actually right. That gave us 34 results at the end. And with those results, we did some analysis. So first of all, we found that those are actually arranged into 3 clusters. There is a first cluster, cluster A, which is about quality control on the product level. So here TDA is used, I don't know, to analyze deficiencies in the shape or the textures or on the surface, something like this. Okay. We have a next cluster, which is about quality control on the process level. So not the product that is produced, but the process that is producing the good. Like use it for detecting chatter and NC machining, so vibrations in the machine and stuff like this. And the third cluster is actually about manufacturing engineering. This is the engineering discipline that allows you to build machines and production lines and processes and so on. Okay. So about scheduling problems and process optimization and predictive maintenance and stuff like this. This was actually the largest cluster with 13 papers. Then there was quality control and product level with 12 papers, and another cluster with 9 papers for the sorry, there's some typo. Product and process, right? No typo. And here we have our 3 methods, like precision homology, UMAP, and map algorithm, and those are now related to the clusters. The thickness of this graph, so to say, of this bar, tells you how many papers there are. The largest method cluster, so the way say, was precision homology. Okay, so far so good. What we then did is we looked at the year of publication. There we see there's some increase, but the numbers in total, of course, are very low. So 2024 is very low because we did this data gathering on April 23rd in this year. And there might also be a bunch of publications that haven't been yet indexed. Yet they would contribute maybe also to the 23 bar. It's unclear, right? But this is sort of, yeah, the shape we get. So precision homology has, I would say, some consistent increase. UMAP first appeared only in 2021, which is natural because the method was published in 2018. Software is available since end of 2017. So yeah, that is something you can expect. And mapper is very underrepresented. Only four works in 4 different years. Yeah, we could speculate whether this is maybe due to patenting issues or what the reason might be. It's unclear. This is probably due to COVID pandemic. Yeah, speculation. Okay, another thing we looked at that I find interesting is the data on which those methods were applied. Okay. So this is to be read as follows. Here is the column of point cloud applications, a finite subset of the RN. And in the cluster A, we have 2 works with where persistent homology is applied to point clouds. And it's applied to certain variety of data. So point clouds, time series, scalar fields in different forms, like microscope images of surfaces, or silicon wafer maps, something like this. 2 works where graphs are the underlying data, and 1 work where textual data, log books, log files were actually used with UMAP as application, or as the method, sorry. Okay, so what we see here is 17 out of 34 weeks, 34 works are concerned with time series. It's the most popular input data to TDA methods. Okay, so I don't want to dig too much into that and waste time here. So a quick summary could be of this larger survey. The numbers of applications is quite low when you compare it to biology or medicine, right? So just go on the donut database by Barbara and so on, and you will quickly see that number of applications here are much higher. Secondly, the most prominent data type, as I said, is time series, and there are a few other findings, like mapper is underrepresented. There's actually no UMAP application for quality control on the process level, which is probably some research gap here. Persistent homology and UMAP is used on a diversity, on a whole variety of data types, but mapper only on 3, on time series, with 3 works, and 1 exception, scalar. Okay, so I want to focus on that, actually, the time series thing. And the question is whether this is to be expected or not. I think it is to be expected, right? Let's have a look at the industry, right? I think the key scientific disciplines in industry are physics, and there it's mostly mechanics, electrodynamics, and thermodynamics, maybe also optics and acoustics. The 3 dominant ones are mechanics, electrodynamics, and thermodynamics, in my opinion. Then we have electrical engineering, control theory, and signal processing. And these, I think, are the fields you erect industrial automation on top. That's it. And those fields are about differential equations, time varying values, signals, and so on. It's in their very nature. So we could summarize it as follows. I think, my opinion, industry is about studying, controlling, and designing dynamical systems and processing signals to the end of controlling dynamical systems and studying. So when we ask how TDA is useful, I think we should ask how can we leverage TDA for time series, which comes in form of signals or trajectories, and how can we leverage it for dynamical systems. And this is essentially what we did in the last 2 years to some extent. So one work I want to report on now is about learning dynamics with persistent homology. And in control theory, we would phrase it differently. There we would say how to perform system identification with persistent homology. Okay, so this is based on a paper we did last year, NeurIPS 2024. This was mainly driven by Roland Quitt's group with Florian Graf and Sebastian Zeng, who was a PhD student back there. Roland Graf is a postdoc. Sebastian then joined my research group for a year, and yeah, we collaborated very closely, and now he is in Sweden. And yeah, so what did we do there? We did the following. So the problem formulation is as follows. Consider a dynamic point cloud and assume it is governed by some dynamic system, some parameterized dynamic system. So you have a few parameters that change the behavior of the dynamic system. And if I give you a finite number of observations, a finite number of point clouds. Can you tell me what the parameters of the dynamical system were? What were the values? That's the problem. And applications would be, there are a ton of applications in biology, like bird flocking and fish movements and insects, but also cell motions in biology or particle systems in physics, and so on. And one observation here is that these dynamical systems, so the law of motions that are somehow incorporated here, they lead to certain geometric patterns emerging due to this attraction, repelling behaviors, and so on. So TDA should be useful, and it is, and it has been used before. So this is not the first work on this, by far not. But we could improve the state of the art, and I will tell you how. So maybe let's formalize the problem a little bit more. So we have a dynamic point set, PT, finite point set. In Euclidean R3, T is the time parameter. And that means for us the following. So let's say this point cloud contains m points, and the xi as a function from algebra 3 as curves, as trajectories. They are the trajectories of the ith point. Dynamical system now means the following. The velocities of the points are controlled by a function f with p parameters that gets as inputs the points and the velocities and outputs the velocities of the points again. So this governs the motion and the evolution of the point cloud. This is the dynamical system. So f is the dynamical system. And maybe you will also add some stochasticity, like, I don't know, Brownian motion or something. So what you get are now observations, p of tau 0 to p of tau n at some time points tau I, might not be equidistant. It might also be that the cardinalities of the point sets might change. Think of some occlusion, or some points leave or re-enter the scenery you're investigating. You also don't have the correspondences between the points. You don't know how the points move. You only have the point sets, no intercorrespondences. The question is now, given those point sets p, can you tell me what the betas were? What we did is the following. So over t, over the time, you have these observations, and the first thing you do is you vectorize the point clouds. So one thing you could do is use PointNet plus neural net. That gives you an output vector from the neural net, which is a vectorization. Another thing you could do is consider RIPS filtration, consider maybe the H0 diagram, so the zeroth dimensional persistent homology diagram, vectorize it somehow. We used the paper of Hough et al. And also gives you a vectorization. And you can stack them together, which is our joint version. Okay? This gives you those vectorizations. Every point cloud gives you a vectorization. So what prior work did a lot is investigating the dynamics of this vectorization. But this is not what we do. We do something different. We assume there is an underlying latent space where we could actually investigate the dynamics. So let's say you can map this trajectory of the point cloud, this dynamic point cloud, into a latent space, and then this PT becomes a path Z in the latent space, some latent path C. And that you can sample at instances of time. So Z of tau 0 would be the encoding in the latent space of V of tau 0 and so on. And then what we do is the following. So this whole path in the latent space, this is what we take to phrase a regression task against our betas. Okay? And for the path, you use some summary information, like you equidistantly sample it, for instance. But you don't only use those encodings, but you can now sample it if you would know the path. Okay, this should be more informative. Okay, so in order to do that, we do the following. You build up a generative model where you use a neural ODE to model the dynamics in the latent space. And you need an encoding here, where we use an mton. This mton gives you the first point here of the path, so C of T0, so to say. With the neural ODE is, you perform a forward integration, your Euler method, for instance, in order to obtain the whole path. That's the idea. Then you set up the auxiliary regression task, and that's it. And that enables us to beat the state of the art. So we tested it on 3 data sets. 2 are mentioned here in this table, the Sona and Vischeck. These are some particle systems. They are each governed by 4 parameters, so beta 1 to beta 4, so to say. And we checked it against the prior state of the art, which was path signature kernels and Crocker stacks. And we checked against 2 evaluation metrics: variation explained, which is similar to R2 in regression tasks, and SMAPI, which is sort of down to the regression task. You measure how far the real betas were away from the betas you predicted, and then you have to scale it because the scales of the betas are different. This essentially gives you the SMAPI metric, so to say. So SMAPI should be low. Variation explained should be high. You want to explain a lot of the variation of your results with this model. And in any case, we're able to beat the state of the art. So we outperform the state of the art. We also scale a little bit better if observation sequences are high compared to Crocker stacks. We perform much better actually compared to the path signature kernel. I don't know, like a factor of 3 better or so. We also did a bunch of ablation studies, not mentioned here, but for instance, we had one study where we checked that persistent homology actually gives you complementary information. Okay, so this is about point clouds, but where's the industrial automation here? So this, I think, this method, this idea has potential to be translated to automation industry. Assumption is the following: consider an industrial machine or a production line or a whole factory. And then I think it's fair to assume that at least it can be sufficiently modeled by a dynamical system. Okay? And this dynamical system is, again, depending on some parameters. Let's say some friction parameter or some value that tells us something about the thermal conductivity or something like this. Okay? And you have observations of the system. So the rough setting is, again, you have parameters influence the system, you get observations, and you can predict the parameters again. So, next assumption. Say you have an anomaly that is caused by some parameters having changed, like the friction parameter increased. And this is anomalous. Then the technique from before sort of gives you the ingredients to do the following. You simply estimate the parameters, and when there are deviations, you don't only have the signal for there's an anomaly, but you can also name what the root cause was, like it was beta 17 that changed, something like this. So this is sort of the motivation why we are interested in the neural persistence dynamics. Okay, another thing I want to talk about is about multivariate time series using persistent homology. Okay. So very often, very quickly, you come in the situation that you want to process multivariate time series. One standard problem is the following. So assume we have such a time series X, which I formalize as a map from an interval to Rm. Let's say it's from a machine of discrete automation. So you have cyclic behavior. Okay? So the question is, how can you decompose the I into its cycles, so to say, right? Into its repetitions of this repetitive behavior. Meaning, you want to tell what the T0 till Tk were, such that the intervals II formed by Ti-1 till Ti are the cycles of this repetitive behavior. The tau I as the length of the interval would be the cycle length. Okay? Very natural to ask this, to to generate some data sets or to ask whether the last repetition was anomalous or stuff like this. The only thing is that actually you have different notions of cyclic behavior if you look at this. Could be that machines have varying speed, so you sort of break the notion of periodicity. It might be that machines have different modes of operation or other abnormalities. So in the state space, you have some forking behavior, so to say. So it's clearly not periodic. And the notions we introduced are three notions. Periodic, which is the one we know from school, like it really repeats itself in periodic sense. We have repetitions, where you also accommodate for reparameterizations within a cycle. So the machine could stop, accelerate, and so on. But in the state space, the hose stays the same, the geometry stays the same, the image of the curve remains the same. The third notion, the most general one, would be recurrent. Like you have a point that you revisit all over again, where your production cycle starts. But on the way, it might have different ways to proceed. But it comes back to a first state all the time. And you can formalize this more mathematically, of course. So we call x periodic. X of t plus tau is x of t for all t. And then in our notion, all ti would be the same, namely the tau. Okay? And there you have the machinery of signal processing from the past 100 years, like Fourier transform, autocorrelation, Laplace, and so on and so forth. We call x repetitive if for every such cycle you have essentially a reparameterization from the ith cycle to the first cycle, such that, you know, if you compose x with gamma, you get x from the ith cycle to the first cycle, more or less. Okay, so this allows for this reparameterization per cycle. And the third notion would be recurring, where we simply say every time you revisit x, so x of t becomes x of 0, so you consider the kernel of x minus x of 0, this gives you the set of the ti's, so to say. Okay, so this allows for variations in the image of x, like different production modes. Or, you know, if you change the friction a lot, then you have probably some shifts in state space, something like this. But that doesn't suffice. You have data here from the real world, you have measurements, you have noise or other sort of deviations. So you need some approximate notion too. In our case, we say x is epsilon approximately periodic or repetitive. If there is a periodic or repetitive x hat that is close to x, epsilon close to x in the supreme norm. Okay. And if you try to do the very same for recurring, this is bad because you come back to x to 0 maybe with very small cycles, and they are sort of noise in terms of repetitions. You want to get rid of them. So when you come back to x of 0, you want to make sure that you left x of 0 in sufficient amount. Okay, and we call that epsilon delta approximately recurring. If x of ti is epsilon close to x of 0, so you come close to the vicinity of x of 0, but within the cycles, you get sufficiently far away, like get farther away from x of 0 than delta plus the closest point to x of 0 within this repetition. So this notion is very natural from a persistent homology point of view. It is lent from persistent homology, so to say. Okay. This allows us now to present three methods for detecting these repetitions. Method 1 is the most general one for recurring.
Could I ask a question?
Sure.
For the last definition, why do you need the point to be a weight delta? Like if I just drop this, then it would still be a good definition. I would still be repetitive if I have something like this. I don't understand why I need this. Like
So say,
because it means if it's just noise, I just stay there, right? And then I can choose any t there, and it would be a good point of repetition.
You get sort of fake repetitions, right? You want to have something like, this is your first repetition, this is your second repetition, this is your third repetition, and so on. If you add noise now, then once you cross close to x0, it might be, it might be that you get very small cycles that just escape the epsilon vicinity, but only a little. And you don't want to count this as a full repetition. But you want to, for let's say a whole production cycle should express itself as leaving the start state significantly. Otherwise, you simply stayed within the vicinity of the start point too much, so to say. Did I make it clear sufficiently?
I understand what you want to model, but maybe I don't understand where this is going or like why this is needed. Because if to my eyes, if this is noise, then it doesn't really matter that I went away. I might as well stay there. And then all of these points on the small loop are good recurring points because I'm just still there. I didn't do anything.
Later then, we
like
will
for
compute
somehow, for you, it makes a difference if I leave a bit, as in like, oh, I leave, so I'm not there anymore. But like, I didn't leave enough, so I also don't want to count it. Like that's somehow like two different ways of leaving. One is good enough for you to start a new cycle, but the other one is actually not good enough to start a new cycle, but it's good enough for you to say this is not a recurring point. And this is the thing, the discrepancy I don't understand. How can it be something sort of in between there, good enough for one, but not good enough for the other?
So we have a notion of significance of a repetition. And if you want to have a lower bound on the significance, this one-to-one translates to a lower bound in the persistence of a point in the persistence diagram. You want to have sufficiently persistent repetitions. Does it make sense more? Does it make more sense now? So at the end, we will draw persistence diagrams.
Maybe in the end, if I see how you model this with persistent homology, maybe it makes sense then how the second parameter enters. Thank you.
Good. You're welcome. Method one is the most general one. There, you see the answer is sort of already. So let's say you have such an X, which is epsilon delta approximately recurring. Okay. Then the method we propose is sort of a baseline method, you could say. Maybe the simplest you can think of. You consider a surrogate function v of x that simply measures how far did x of t move away from x of 0. Right? The norm of x of t minus x of 0. And this is plotted here. And you are interested in the local minima that are close to 0. But but still have a sufficient persistence. Right? If the surrogate function looks like this, you want to drop them because they are not like fully featured repetitions. It is like, yeah, it's not persistent enough, not significant enough. It's sort of a design decision in the modeling. Okay. So you take the surrogate function, you consider the sublevel set filtration, you compute H0, which gives you this persistence diagram, the zeroth diagram. And then you're interested in the points where the birth level is at most epsilon, so you get close enough to the starting point, which means, this area, and where the persistence is at least delta. So you don't care so much for points down there, but which are sufficiently persistent, which would be now this area, the intersection. So these are the points you're interested in. Okay, these are fully fledged repetitions because they left the starting point sufficiently using this notion, and they came back to the starting point sufficiently using this condition. That's the idea. And so the TI are those local minima identified here. So you also need the linkage where the components were created during the sublevel set filtration. And this gives you stability in the topological sense because this inequality holds. But there's a downside, namely, say for some reason you would have repetitions that looks like this, right? And by this notion, you would have a first repetition here, and a second repetition here, and a third repetition here, and so on. But say for your application, it's quite obvious that the full 8 would be one repetition, which in our notion would mean if you consider epsilon approximately repetitive, but epsilon approximately self-intersecting trajectories, and you want to consider the full 8 here, so to say, as a repetition, then this method 1 would accidentally tell you this is one repetition, this is the second. That might be fine, but for other applications it might not, which motivated us to extend this method. Which brings us to method 2. Let's say X is an epsilon approximately repetitive time series. What we now do is the following. When we have such figure 8 shapes, we need to somehow disentangle when we approach it from here, whether we came from the bottom or the top half of the figure 8, so to say. And you could do it by considering maybe slopes or so, like differentially quotients or so. But I think the more natural way to do it, the more stable one, is take an embedding, so time delay embeddings. So we consider another function, ux, which simply performs the time delay embedding, like t is mapped to x of t plus delta, and so on, for a certain embedding length, which disentangles these ambiguities at self-intersections. And then you again define the surrogate function, but now on this larger space. Maybe use some sort of a p-norm like this. And then you repeat as in method 1, so to say. So you again filter, check for points in this area of the persistence diagram. That's it. Okay. You again get stability. So some math, you see that this is the Lipschitz constant here. And that's it. The downside here is, from a practical nature, that you need some parameterization for the time delay embedding. You need to make a choice for delta and for d. And it might be unclear how to do that. You could come up with some heuristics or whatever. Or we could think of another method. This is what we did. Method 3. So we have another method, but we now require more structure on the time series. Namely, we consider epsilon approximately periodic time series. The idea for method 3 is the following. So before, x0 is sort of a pivot element. We all relate to x of 0 when this reoccurring happens, right? What about considering all possible pivots instead? Or in terms of a time delay embedding, you have sort of a holistic time delay embedding where the embedding covers the entire time series x, so to say. Okay? So we become sort of independent of the choice because you covered everything. So that means the following. In other words, we consider the recurrence function, which is related to recurrence matrix, dynamical systems, and so on. So a function w of x, where you plug in pairs of timestamps and compute the pairwise distance in your Rn. Okay. And what we then do is we again construct the surrogate function, but we average along fixed time delays deltas. So the surrogate function at delta is the recurrence function at t and t plus delta averaged over all t's. That smoothens out stuff. And we consider sort of all possible pivots x0 by this way. Okay. This again gives us stability by this chain of inequalities. But again, comes with a downside. Namely, as soon as your time series deviates from periodicity in a sufficient way, then you get into trouble with this averaging here. And then this surrogate function looks different, and yeah, you will get into trouble. But these are the pros and cons of the 3 methods. So maybe some summary, maybe some evaluation actually. We generated data sets. There are no such data sets now, but we can generate one because we have this testbed. We generated a multivariate data set from an injection molding machine. We have some 4.15 million samples, some 23 variables recorded, and displaying some production process with cycles, the cyclic behavior. Each cycle comprises 25,000 to 35,000 samples, some sample rate of a kilohertz, So per millisecond, we have a sample. And we designed the data set in a way that this periodic, repetitive, recurrent behavior is displayed. So in total, the data set comprises 120 cycles. And the 120 cycles are grouped into 18 modes of operation. There are 20 cycles showing periodic behavior. Then there are another 20 cycles, hence 2 times 20 cycles, with periodic behavior plus noise. Then we have 10 groups of 5 cycles where we vary the injection speed, plastification speed in the injection molding process, or the clamping of the tool is delayed, stuff like this. And we have another 6 groups per 5 cycles, another 30 cycles, where we increased friction and so on, which leads to recurring behavior. Okay? And we couldn't check against other methods because we are not aware of any. But I think the summary is the following, right? So what we did here is not rocket science. It's very simple, but it's very useful too. So we took sort of the simplest idea we can think of, enhanced it with persistent homology, and get something very useful. And that we then further enhanced by adding time delay embeddings or recurrence functions. That's sort of the story, right? It's not rocket science, but it's very useful. Also for our company partners. Okay, so I talked about the industry, I talked about dynamical systems, I talked about multivariate time series, and now I want to sort of finish up with a few ideas on the relation between persistent homology and the industry. And by talking about detecting peaks in dual spaces. This idea works as follows. So the observation is persistent homology is useful in a variety of applications, and it's complementary to existing techniques like autocorrelation and Fourier for system identification, something like this. Okay? But the dissemination industry is lagging behind. I guess it's because the people knowing the problem space, the people knowing the solution space, they are largely distinct. Seldomly people work in both areas. So the idea is, how can we foster that? Or is there a way to come up with applications maybe systematically? So I think one way, maybe our survey paper contributes to dissemination, but another idea could be the following. So different application fields, they have very natural dual spaces they operate on. And very often we look at peaks in there, or maybe also at cycles in there. And then TDA can be useful. I want to give 2 examples. Peak detection in Fourier spectrum in signals, and peak detection in Hough space for line detection. Okay. So the first thing goes very quickly. I did that actually when I was in industry. I was in industry for 5 years and then moved back to industry. And there a colleague had the following problem. In closed loop control theory, in particular in motion control, we want to do controller tuning, tune the parameters of the controller. In order to do that, we need to know the natural frequencies, the resonance frequencies of the system that is controlled. So what's done there is the following. You have an excitation signal at the drive, at the motor. You get some systems response. You consider the Fourier transform, which looks like this, and you want to identify the most significant peak, which is easy with persistent homology and very difficult if you don't do it like this, because then you add all sort of heuristics and smoothing and so on. Okay? This is what I did there. This was a low-hanging fruit, and it's super performant, right? In n alpha n, it's done. Okay? Another example is the following. Hough transform. This is something we submitted these days. Yeah, I dare to tell you about this already. Hough transform is a technique in pattern recognition, computer vision, to detect lines and images or in point clouds. It also works with a dualization. Does the following. You can parameterize a line in Hess normal form, like distance to the origin, orthogonal distance to the origin, and the angle by which the line is rotated. This gives you, so to say, the Hough space of lines, the space of parameterizations of all possible lines. When you consider all lines through a single point, you get in Hough space such sign functions, like the set of lines through this magenta point is set of points in Hough space forming the sign. And you can do this with all 3 points. And the intersection in Hough space corresponds to the one line in common to the 3 points. So in an implementation, you discretize this, then you have some histogram, some voting scheme, and ask for the most dominant peak. The classic approach, how it's implemented in OpenCV, this is the standard approach, is thresholding. And that's bad when you have noise or uneven sampling of lines. And what we propose is persistence-based peak detection. This looks like this. You have 2 lines here in the image space. They are sampled unevenly. And you add noise. And the Hough space looks like this. Set of all lines through all those points. And then you do some voting. You want to identify the most prominent peaks. The persistence diagram, it looks like this. So sorry, those axes are swapped. The diagram is correct, but it's just an unusual way to display it. So what OpenCV does is, in this super level set filtration in the Hough space, is thresholding at the birth level, like this. And no matter where you choose your threshold, you won't identify only those 2 points, but you only identify this 1 point at this threshold, and if you lower it, you get some false positives. And you add heuristics to remove them again, right? But the better idea, I guess, is doing the thresholding on the persistence, not on the birth level. But you only can speak about it once you talk about persistence diagrams, right? So that's the idea. Okay, some final slide, my last slide. I think industrial automation is an important field for our society and our wealth. You have these industrial revolutions, the first, the second, and so on. Our modern society heavily relies on that. And TDA can be useful for it, right? TDA has potential in engineering and industry, but the dissemination is lagging behind. I think if you want to work on the foundations of industry using TDA, then you should focus on the dynamical systems and time series. This is just a natural way to do it. Those are the foundations of industry and engineering and so on. Then you can do the forecasting, the classification, and pattern recognition, and so on. Another way to look at it is TDA is used a lot in supervised learning, unsupervised learning, and also self-supervised learning, and so on. But to my knowledge, TDA is not used a lot in reinforcement learning yet. But this will be interesting because reinforcement learning is the machine learning counterpart to control theory. And this is important for industry. So reinforcement learning is sort of the next generation methodology for industrial automation, in my opinion. Okay, and the third thing I talked today about is let's consider dual spaces in the respective application domain and see whether we could apply TDA there, because there should be a lot of low-hanging fruits. So what's next? So in our case, we have a realistic test bed. We have people who know how injection molding machines work and how industry works. They build up this test bed. We can generate data. We have a very interdisciplinary team. And we would like to cooperate. Okay? We have a bunch of people who know a little bit of TDA, but this is homology. I myself are into this field for 10 years or so. And we want to connect those 2 fields. And if you want to contribute, want to cooperate, just drop me an email. Our primary research interest here, not entirely bounded to this, but this is our focus, is anomaly detection and generative models for multivariate time series and dynamical systems and so on, stemming from discrete automation. So we have this repetitive behavior. This is sort of our core, but we do all kind of stuff like Hough transform. And that's it. Thank you.
Thank you very much, Stefan. Let's all unmute and give Stefan a round of applause.
Thank you.
Right. Yeah, pardon me?
So that's an awkward time series from industrial automation's point of view. It's not repetitive.
Yeah, and unfortunately, this is what happens in these online seminars. But I think
Right. Yeah.
it's all just the new world. Now, do we have any questions in the chat? I don't think so at the moment. So maybe let me get started with a bigger one, since you already mentioned the next steps. Do you think that TDA, or in general, say topology-based methods, what kind of future do you foresee for them in industrial applications? Because this is really interesting. We are searching for this application, right? We're searching for the nail that shows that the TDA hammer is good. So where would you see this now?
Wow, that's a very big question.
Sorry about that.
So my humble thoughts on that are the following. So I think there are a few interesting position papers that highlight directions. Like at ICML last year, there was a position paper on topological machine learning. Michael Kerber wrote an interesting, a nice paper about the future of persistent homology and TDA and what are the open problems in the field, multi-parameter persistence, and so on. So that's one way to look at it.
Mhm.
Another way to look at it, I think, is the following. So I talked about these dual spaces, right? And at least in signal processing, the most prominent dual space is the Fourier space. So you have a time signal, do a Fourier transformation, and this Fourier, in the Fourier spectrum, you see the spectral decomposition from an engineering point of view. That is very valuable, right? The nice thing, we have similar thing in TDA too, or in precision homology, right? You have some data, you have some underlying geometric structure, and then you have a topological point of view on it, using barcodes, persistent homology, or whatsoever. What we don't have is the way back. So it's not a dualization. This is like sort of a topological projection information-wise. You cannot reconstruct the data. Fourier transform can do that. You have the inverse Fourier transform. So maybe we could think of, if you have this, I don't know, oversimplification of you have data and a few directions of information is persistent, can you add the other directions too in order to be able to reconstruct the data? Is there some full forward and backwards transformation pipeline in a TDA setting? This could be interesting. And another thought of mine is the following. So, but correct me if I'm wrong. So there are many people here in the audience, I think, who know much better than me. I observe that very often when we apply persistent homology, we do this on point clouds. Even though the original underlying object was not a point cloud. There's tons of works on multivariate time series and establishing counting the cycles in periodic signals and quasi-periodic signals. Perea et al., for instance, Uli Bauer recently had a paper, and so on. They very often sample the multivariate time series, get a point cloud, maybe also consider the taken embedding and have a point cloud, and then consider RIPS filtration. But then you lose the temporal dimension. The original underlying object was the multivariate time series, a function from a real interval to Rn. And we should, I think of a filtration based on the original object, not on the sampling.
Yeah, in particular, we should not throw away information. Pardon me for interrupting, right?
Right. That is my gut feeling, at least, right? We should preserve most of the original information and ask for the natural filtration of the underlying object. It is just that in practice, we have this software ecosystem. We have RIPSA and all the software packages in R and Python and Giotto and so on. And a lot of energy ran into developing the software packages, and they are fast and bug-free and so on, right? So it's, I think, just easy to do it this way. And I don't know whether this is one reason, right? But maybe we shouldn't do it too much.
No, I understand that. Yeah.
I mean, and this is also, I think, a reason for the success, right? I mean, if I bring an analogy, right? When I started computer science, I actually did a sort of a major in what we then called natural computation, which would now be machine learning. And every institute re-implemented their neural network simulator. It was called back then because we simulate biological networks. And this stopped some 15 years ago because TensorFlow came and PyTorch came, and this accelerated research there. You don't implement your backpropagation or your order differentiation framework. You just use it. And you have highly optimized optimizers like ADAM and variants. And you have all these tools for data cleanance, and you have NumPy and this machinery which accelerates research. And we have a similar situation in TVA, right? With these software packages. I mean, they are a bless. But it might lead us to easily use point clouds, for instance, when we shouldn't. Maybe, but happy to hear opposite opinions, because as I said, I think experts here know better than me.
I mean, in some sense, the tools shape what we can do with them, right? So no, I understand that.
Yes. Yeah, absolutely. Yeah.
But it's also hard in a way to deal with the time information in a natural fashion, right? Because to stick with your analogy about the software that we have, I mean, it is very tempting to just treat time as another dimension, right? And maybe the physicists would now say, well, of course it is, right? But it behaves differently than other attributes because you can probably you cannot move backward, right? So some type of distance information that we would be doing would semantically map to something that we don't necessarily want to do. This is an even bigger thing, but I don't want to get into trouble for saying this about ML, but when you encode all kinds of variables that you shouldn't encode, right? Yes, you can vectorize everything, but it doesn't mean that it's good to have it as a vector. Yeah, but very exciting stuff. So do we have any other questions towards the end? Maybe a short one. If not, then I'm going to stop the recording and we can move to the offline session and close this and close the seminar for today. But thank you very much for being here, Stefan.
Thank you very much for the invitation. I hope it was interesting.